This is anjir.
Oh,
Oh, record. Okay.
yeah, I record.
Okay. So this is more like we like study together, yeah. Not like I'm the teacher, but if have problem, just ask me, yeah. So we
Okay,
do
okay.
we do two chapters. We do two chapters ya,
Yeah,
biar lebih panjang lah. So atoms, elements, and compound dulu ya. Chapter
yeah.
3. I don't know harus English atau apa. English aja lah.
Okay.
Ya, ayo belajar belajar tuh gitu. Anjir. So chapter 3, atoms, elements, and compounds ya. So Owen, what is atomic
Yeah.
structure? Read it.
Atomic structure. Uh, Atoms are the smallest particles of chemical element that can exist. Elements are substances that are composed of just single types of atoms. For example, the
Okay,
element of okay.
okay. Wilbert, you continue, Wilbert, for the example.
For example, the element carbon is made of only carbon atoms. Likewise, the element oxygen is made of only oxygen atoms. You get the gist.
Yeah. So the structure of an atom is made out of three atomic particles: protons, neutrons, and electrons. So this is the electron, this is the neutron, this is the proton. Proton, yeah.
Okay.
Uh,
Okay. So that is the example of a helium atom, ya guys. And then first, the location dulu ya. Protons and neutrons are always found in the nucleus. Electrons are found in the shells, or they orbit the nucleus. What now say the charges? Hello,
uh,
hello.
Hello, yeah.
Yeah,
uh, the, the charges, right?
yeah.
Okay. So charges. The proton have a positive charge, of course. The neutron have zero charge and or neutral, and electrons have a negative charge.
Okay. Now, Wilbert, say the maths. Yeah.
The protons have a relative mass of 1. Neutrons have a relative mass of 1. Electrons have a negligible relative mass of 1 over 1840, which is essentially zero.
Yeah. So this is just a summary. Name, electron, symbol, E, that's a minus, but it's small. The charge, -1, relative mass, 1 over 1840. Name, proton, symbol. Yeah, you get it. So now, and isotopes are atoms with the same proton number, which is just the same element but different neutrons, okay? So
Yeah.
this is the periodic table. Yeah. There are many chemical elements on Earth. Jesus. Uh, so Owen, how much elements are there?
Uh, there are a total of
It's there.
118 elements. The periodic table.
Good job.
Yeah.
Okay. Jesus Christ. Okay. So the example helium, yeah. So this is how you do it. So this is the proton, the number. This is the chemical symbol of helium, which is He, and this is the mass number, which is 4.003. So firstly, it tells you the full name and the shortened chemical symbol for the element. In this case, helium, which is He. This is fairly straightforward. Oh, and say the next paragraph.
Secondly, it tells you the proton number and the mass number of a helium atom. Here are a couple of extremely important things to remember.
Okay, Wilbert, your turn to say the important things.
The proton number,
Or
aka the atomic number, is the number of protons in the atom. The mass number is the total number of protons and neutrons. Recall that neutrons or protons have mass, but electrons do not. The number of electrons will always equal the number of protons. An atom
Okay,
always has zero overall charge.
okay. So I'll continue that. An atom always have a zero overall charge because the number of protons will always be cancelled out by the same number of electrons. If there was an imbalance, then the atom would become charged, and at that point, it will not be called an atom. Instead, it is called an ion. This will be converted down below. Okay, so yeah, from the periodic table, you can just calculate the number of protons, neutrons, and electrons of any element. Yeah. So let's just take oxygen for examples. So oxygen it has 8 protons. This means it has 8 electrons. Since its mass number protons per neutrons is 16, it must mean that it has 8 neutrons, here, guys. And then Owen, read read the
yeah,
electron
the
arrangement.
electron. The electron arrangement. Recall that atoms are held in shells. Shells are represented as rings around the nucleus. It is really important to understand that the maximum number of every electrons that a single shell can hold can vary. You can look at that in the diagram as well.
Okay, so this is the diagram, yeah. So in the middle is the nucleus, the first level, or like yeah, the first level. Let's just say level. So the first shell. The first shell can hold only 2 electrons to make it stable. The second, 8, and the third will be 8. Yeah, like as what I described. The first, which is the inner shell, can hold 2, and the second and third can hold up to 8. So let's take oxygen as an example again. Above, we established that a single oxygen atom holds 8 protons, 8 neutrons, and 8 electrons. Remember, electrons always fill from the inner shell first. Since we know that the first electron shell can only hold up to 2 electrons, it must mean that the rest of the electrons, which is 6 of them, are held in the second shell. This is what an oxygen atom, therefore, it would look like diagram. Yeah, that one. So it will look like this here, guys. Okay, okay. So the goal of atoms is to be is to achieve a full outer shell of electrons. So reactivity of the elements. Wilbert, can you please read the reactivity of the elements?
Okay. Activity of elements. As mentioned above, all atoms have a simple goal of wanting to achieve a full outer shell of electrons. If you look at the diagram of oxygen above, you will see that an oxygen atom has 6 electrons in its most outer shell. So have a think about it. How could oxygen achieve its goal? There are possible in two main ways.
Okay, Owen. Now say that. Can you read the two main ways?
Okay, the first way, which is kin to electrons. If an oxygen atom just added two extra electrons into its outer shell, then it would have eight, and therefore a full outer shell. Or you can lose two electrons. If an oxygen electron lost all six of its outer electrons, then that shell would simply disappear, which means the inner shell, with the two electrons, will become the most outer shell. This would mean that indeed the atom would now have a full outer shell since two electrons is the maximum for yeah sorry
Yeah.
for that shell.
So for you guys, which is easier? Option one or option two? And why?
I feel like
With you there, Owen.
I feel like option two is better. I guess. Yeah, I
Okay.
feel like option two is better. I will use for electrons. Yeah, I feel like
Okay.
they'll listen to it, right?
Now you will, Wilbert.
Yeah.
Tell me which one would you think is better?
Uh, um, Also number two.
Oh, okay, okay. Let's see. Let's see what they think of that. So they think that that option one is easier. Gaining two is not easier than
Yeah,
losing six. So because you can gain two extra electrons by just sharing it, and you can lose six of them by by sharing it too. So yeah,
yeah,
it will be covered later in chemical bonding. So some of them already have full outer shells. So they're called noble gases, and they're normally the most right one, the most right hand side of the table, which is which are these it's these ones. Okay?
yeah.
Okay. So now, yeah, chemical bonding. Okay, there are several types of chemical bonds that we will be looking in this section. We will be looking at ionic bonds, covalent bonds, and metallic bonds. Before we get started, let's get some definitions straight. So, Owen, read the first and second
Uh,
one.
First, yes, okay. So elements, yeah. Elements are basically are substance that are made of one atoms, and then we have compounds. So compounds are uh, on the other hand, yeah. So compounds are basically substances that are made of chemical bonds between two or more elements, like group of elements.
Okay. Now, Wilbert, can you read number three?
A mixture is a combination of two or more different substances in the absence of chemical bonds.
Okay. So, when atoms lose or gain electrons to obtain a full outer shell, the neutral charge will change. So, if it's disrupted, it will be disrupted since the proton number will now be unequal to the electron number. So, if that happens, it's called an ion. So, it could be a positive or negative. A positive is called cation, and a negative is called an anion. And metal atoms lose electrons to form cations, and nonmetals gain electrons to form anions. So, later, nonmetal will have a negative charge, and metal atoms will have a positive charge. Okay, and then
Okay.
they're also since cations and anions have opposite charge, they are attracted to each other like magnets to each other via strong electrostatic force. This is called ionic bonding. Okay, Owen, please rate how it works.
Okay, so here's how ionic bonding works. So, metallic element will donate their outer electrons to a non-metal electrons that that need it. Both elements will therefore achieve full outer shell and turn into cations and anions that get bonded by electrostatic forces.
Okay, now Wilbert, can you read us the first example?
Okay, example one. Group 1 is simply the first column of the periodic table, likewise group 7 is the seventh column. More will be learned about in a separate topic. Elements of group 1 metals in group 7 nonmetals in the periodic table form ionic bonds. This is because group 1 elements need to lose one electron to be happy, whilst group 7 elements need to gain one electron. This is a win-win situation. The group 1 metal will simply donate an electron to the group 7 nonmetal, and this will result in the formation of cations and anions that are bonded via ionic bonding.
Okay, so this is an example. So this is sodium chloride, which is NaCl. So there's one extra right of NaCl. There's one extra electron. It will not be complete if there's one extra. So you give that one extra to chlorine, which needs one more to be complete. So you give one. Now and Na or sodium will be a cation, which has a plus one charge, and chloride will be an anion. It will have a negative one charge. So yeah, let's just do one example. So now covalent bonds. So it's only between nonmetals. It's just between nonmetals. And atoms can achieve a full outer shell, electron shell via sharing of electrons. A pair of electrons, one from each atom, can be shared. This is a single covalent bond and it holds the two atoms together. Owen, can you please read the next?
Okay. Please note that some atoms can be bonded via a single bond, like sharing a single pair of atoms. Double bond, or sharing of two pairs, or triple bond, or like yeah, sharing of three pairs. Moreover, covalent bonds will only exist between two non-metals. These examples, the example below uh, show that by sharing electrons, all atoms in the bond successfully achieve a double gas configuration.
So let's just do between chlorine, yeah. So
Mm.
chlorine is the same element, right? And chlorine has how much electrons, Owen? Total, total,
Chlorine
total.
of 1, 2, 3, 4, 5, 6. We have 7. Yeah, 7.
Okay, that's the outer right, seven, right? So
Yeah.
seven. So chlorine is 17. So there will always be two inside. The second shell there will be eight. So there will be 10. So there's 17. So the third shell will have seven. So if you share between two, you'll get eight. See? So one, two, three, four, five, six, seven, eight. It's the same for the other one, which is one, two, three, four, five, six, seven, eight. So now they're now in perfect configuration. So these are the more complex ones, but yeah. So let's just do nitrogen, just the easiest one. So this is what we call a triple bond because there is three in like the middle. One, two, three. And then this will just be one, two, and one, two. So one, two, three, four, five, six, seven, eight. So both of them will have eight. So it's in perfect configuration. So now let's talk about the differences of intermolecular and intramolecular. So the difference is very important because when you're melting or boiling a substance, it is the intermolecular forces that you are breaking, not the intramolecular attraction. So intermolecular forces are attractive forces that exist between one molecule to another. These are usually quite weak. Wilbert, read the next one.
Intermolecular forces are attractive forces that exist between one molecule to another. These are usually quite weak. Intramolecular forces are attractive forces that exist between atoms within the molecule. These are usually extremely strong.
Okay. Okay. So this is an intermolecular bond. It's HCl. So these are the intermolecular, which is the bond between the two elements. These are the intramolecular. The intermolecular is the out this one. Okay? This difference. Okay. So now the differences between ionic and covalent. So the difference is just ionic compound is between metal and non-metal. Covalent is between two or more non-metals. Type of particle for ionic is only ion, and for covalent is just simple molecules. Volatility, which is the melting point and boiling point. So ionic compounds will have high and covalent will have low for both of them. Solubility, ionic is soluble, but insoluble in organic solvents. Covalent is mostly insoluble in water, but soluble in organic solvents. So yeah, then these are the electrical conductivity. And okay, go to the let's go to metallic bonding. Okay, so Owen, can you please tell us what metallic bonding is?
So in metals, the atoms shape their outer electron to become cations. The cations are arranged in a regular lattice structure, whereas the removed electrons are delocalized and free to move throughout the structure. The lattice arrangement of cations are therefore surrounded by free electrons, and since cations and electrons have opposite charge, they attract each other, which other bonds the structure together. Metallic bonding is therefore defined as the electrostatic force of attraction between cations and their surrounding sea of electrons.
Okay, so these red ones are the delocalized one, delocalized electrons, and the positive ones or the blue ones are the metal ions. So now we're done with the first one. We're done with the first chapter. Now we're gonna switch to the fifth chapter. Hey, the fourth chapter. Why did I press the fifth? No, man. So now we're gonna study the fourth chapter, which is stoichiometry. So stoichiometry. So let's do formula of simple compounds first. To figure out the chemical formula of a given compound, all you need to know are the valencies of the atoms that make up the compound. So the valency is the amount of electrons an atom has to gain or lose to achieve the outer shell, the full one. So this is how you know the valency. So group one has one, group two has two, group three has three, group four has four, group five has three, group two. So it's like this now. So group one, one. So you have to gain, eh, you have to lose one. For group two, you have to lose two. For group three, you have to lose three. For group four, it's between you gain or lose. Group five is you gain three. Group six is you you gain two. Group seven is you gain one. And the last one is just yeah, you gain nothing. So now, Wilbert, can you please tell us the next the first green box?
The group of the element on the periodic table tells you how many electrons there are in the atom's outer shell. From this information, you can figure out how many electrons it needs to gain or lose to achieve a full outer shell. Groups 1 to 3 metals will lose electrons, while groups 5 to 7, which are non-metals, will gain electrons. Group 4 can do either. Also remember many atoms will become ions due to the loss or gain electrons in ionic bonding. This means the valency of an atom will also tell you the charge of its respective ion. Sodium is 1 charge, chloride ion is -1 charge, and so on.
Yeah. So once you know the valencies of the atoms, all you need to do is swap the numbers around and cancel them out if they're equal. So these are the examples, yeah. So formula of magnesium chloride, M magnesium or Mg, their valency 2 because they're in group 2. So chlorine valency 1 because they're in group 7. So you have to swap the two around. So it will be MgCl2. The valency number 2, it will go here. And then the valency 1 will go to the Mg. So that's just the first example. So aluminium is the same thing. Oxygen's two valency will go to aluminium, which is Al, and the valency of aluminium will go to oxygen. And oxygen is not called is oxygen called oxygen not O. It's because oxygen is O2 because it's diatomic. So what is the formula? So the formula of calcium oxide. So calcium is 2 and oxygen is 2, so just cancel them out because they're the same. So it will just be CaO or calcium oxide. So writing equations. The skill will be briefly introduced here and developed further throughout the IGCSE course. All chemical reactions can be represented by equations, and you need to know how to write both word equations and symbol equations. So it's just very simple. So for words, it's just magnesium plus oxygen equals magnesium oxide. So now, Owen, can you please tell us how to do the symbol equations?
Oh, sorry. Okay, symbol equations. Okay, this is the most common type. Yeah. Atoms and compounds are represented by their symbol. This is a bit more complex because the equations need to be balanced. A balanced equation means that there are the same number of each set of atom in both sides of the chemical equation. For example, Mg plus O2 becomes MgO without the subscript 2.
Okay,
Yeah.
so as we learned above, you know the chemical formula for magnesium monoxide is MgO because magnesium and oxygen has both two valencies which cancels each other out. So the equation here, this Mg plus O2 equals MgO, is not balanced because the left hand side has two oxygen atoms, but the right one only has one. So why can't the oxygen be written as a single O, not O2? Yeah, yeah, because oxygen, nitrogen, fluorine, and hydrogen are diatomic elements. So they are always found in molecules. Like two of them will always bond together. You will never find a single oxygen atom. You always find two. So we can change the formula of magnesium oxide into MgO2 to balance the equation. We cannot do that. So now, yeah, the formula is MgO. So you cannot really change the 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 original formula. So to balance it, just put two in the front, so there will be two Mg. Yeah, and then later it will be it when it gathers each other, it becomes one. It will be two MgO, and Yeah, this is it's balanced because two Mg and two Os. LH LHS is left hand side, which is this side, and RHS is this side. This is LHS. This is RHS. Okay. So now, Wilbert, can you please tell us the
Mm.
state symbols?
State symbols represent the physical state in which the reactions or products are in a chemical reaction. For example, C3H8 plus 5O2 becomes 3CO2 plus 4H2O.
Okay. So S means solid, like you see the S. Let's just say C3H8. Beside the 8, you see the G, which is gas. So the difference, so L in the 4H2O, that L means liquid. If there's an S, it means solid. If it's AQ, then which is aqueous. So now for the calculation part. So these are the definitions. So at relative atomic mass, or you can just simplify to AR, the R is small, the A is a capital. This is average mass of the naturally occurring atoms on the relative scale, whereby C, a 12C atom has a mass of 12 units. Now, Owen, can you please tell us the definition of relative formula mass?
Okay, relative formula mass. Yeah. This is the average mass of the natural occurring atoms on a relative scale whereby C 12 the atoms are made of 12 units.
Okay, so the definition of mole. So the amount of a substance that contains 6 times 10 to the power of 23 atoms, ions, or molecules. The number, which is 6 times 10 to the power of 23, or 6.022 times 10 to the power of 23, is called Avogadro's number, a constant. One mole of a substance have a mass equal to the relative formula mass. So, Wilbert, can you please tell us the definition of empirical formula?
Uh, Relative atomic mass. Relative atomic mass is the average mass of the naturally occurring
No, no,
atoms.
Wilbert. Not that one, Wilbert.
Oh,
The empirical formula.
okay. Empirical formula is the simplest ratio of atoms present.
Okay. So the molecular formula. So it shows the actual number of atoms of each element in one molecule of the substance. So the molar volume, which is Vm, capital V and a small m, the volume occupied by one mole of any gas at room temperature, and pressure, which is you can just simplify to R dot T dot P. This has a constant, which is estimated to a value of 24.24 decimeter cube. dm is decimeter. Okay. So, or it's not, yeah, it's cubic decimeter. So, Owen, can you please tell us the definition of concentration of solution?
Yeah, the definition of concentration of solution is the measure of amount of solute in unit volume of solution. The units of it is moles uh, per tm cubed.
Okay. Wait, wait. I think we should
Send the recording.
recording.
Okay.
Let's continue, yeah.
Yeah, well, yeah,
So we
guys,
like
continue.
the last one is concentration solution. Does we do?
Yeah,
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 empirical formula, molecular formula. The last one.
I think
No,
yeah.
I
I think
no,
you're the
I
one
think
who said about concentration, right? Now we do mole equations, right?
yeah, yeah, that was me, that was me, that was me. Yeah, I read that.
Okay. Now we'll do mole equations here. So there's so much calculations here. So, but the three-parted ones here, Ajay. So now, first thing we do
Okay.
is memorize the three first ones, the most important ones. So number of moles equals the mass divided by the mass of one mole. Okay.
Yeah.
And the second one, number of moles of gas. This is for the gas divided of volume of gas per cubic decimeter at RTP or room temperature divided by 24. And moles solute equals concentration and then yeah, concentration times volume. So, Owen, can you please read the
Uh,
box?
yeah, good one. Yeah. You must memorize these three equations of by heart, and also have the ability to rearrange them. A lot of the calculation examples below will make use of these equations, so you must be comfortable with these equations.
Okay. So moles and masses. So number of moles equals mass of substance divided by the mass of one mole, which is our first one here. So example one, calculate the relative formula mass of the following. So you guys find a periodic table first for these few examples because you guys will do the example first, then we will see the answers. Okay.
Yeah.
Okay. Now you guys search for periodic table first. In like Google, up to you. And if you want the calculator juga lah, you know,
What?
periodic table and calculator, you can use your I don't know, you can use your phone, I guess it's easier.
And which one we need to do?
Yeah, also, later, there will be others. Later, I just tell you to do it now aja. So later, you guys usah susah-susah cari. So this the three example. See, H4 equals 1 times 12, which is C, which is carbon, and 4 for hydrogen, because hydrogen is 1 equals 16. These are the others. So now calculate the mass of one mole of the following. So do find the mass of one mole of H2O. Kan gampang. Before I do a little bit sneak peek. So yeah, easy. So do H2O,
Uh,
one mole.
the mass of one mole.
Yeah,
Okay, wait,
it's just the periodic table. Don't search in Google.
what's my But
You guys have the answer now?
wait, H2O, right?
Yeah.
30 grams per minute.
How did you get 30?
Wait up, not 30, sorry. 32. 30.
Tell me how you get 32.
Oh, okay. So, wait. Wait. So, so we get it by the mass of what's it called again? Of H2O. So we get the mass of H2O and then over mole, which is like wait, how much is that
No,
again?
no, no.
6.
I think you're trying to use this, right? Mass of substance divided by. No, no, no. We're not doing this yet. We're doing it based on.
Uh,
You're doing it based
uh,
on this. By just getting the atomic mass of both of them and then just adding it together. It's easier now.
the atomic mass.
Yeah.
Voila. Sorry. H2O, right?
Yes.
So, 1, 2, 3, 2, O, 16 plus 1 is like 18. Wait, no. It's 16. Yeah, 16. So, you got 18. Yeah, 18.
Yeah. That's the answer I was looking for. Now,
Oh,
Wilbert,
yeah. Sorry.
can you
I heard
search
it wrong,
me
Lati.
the atomic mass of MgCO3? It's a little more complicated.
Uh,
But pretty,
MgCO3.
still pretty easy.
MgCO3. Okay. Magnesium. CO3. Carbon. CO3 16. 84. 84.
Correct.
Yeah.
Sorry. So now, Wilbert, for example 3.
What?
For example 3, can you please find me how much does 2 moles of hydrogen, how how much how much is the atomic mass of 2 moles of H2O? So 2 H2O. So you get 1 H2O and you just multiply by 2 because there's 2.
Mm.
Can you repeat?
So can you find me same like this, like this? How much does two of H2O? How much is the atomic mass?
The atomic mass of 2.
We already have the atomic mass of one H2O. Now how much is two H2O? So two H2Os.
2 times 18. 2 times 18 is
How much?
2 times 18 is 36.
Yes. Okay, so
So 2 moles is 36 gram.
correct. Okay. So
Okay.
before, because Owen can do the two easy ones. So now Owen,
Yes.
find me half a mole, 0.5
Half a
moles
mole
of NaOH.
and AOH. Okay.
Okay. So can you do it, Bob? Or do I help you?
Wait. Yeah. Wait, what's the formula?
So
Oh,
I'll just scroll down and you see the answer together. So 0.5 moles of NaOH. So one NaOH. Na is 23, OH 16. O is 16,
yeah.
H is 1. You add Na and O equals to 39 because 23 plus 16 is 39. And then you add one
Yeah.
H, which is one hydrogen, which is just 1. You get 40 because 0.5. You multiply 40 by 0.5. So you get 20
Oh,
grams.
yeah.
Okay.
Okay. Thank you.
So yeah, should we do example 4 or should we just read it? What do you guys think?
I think reading is fine.
Read it, yeah. Okay. Example 4, calculate the mass of magnesium oxide formed when 3 grams of magnesium reacts with excess oxygen. There are 4 steps. So, Wilbert, can you please tell us the first step and the second step? And Owen will tell us the third and the fourth step.
Okay, so the first step of calculating a mass of magnesium oxide is write down a balanced chemical equation. And and step number 2 is calculate the amount of moles of the reactant.
So the step number three is calculate the amount of moles in the product. And for step four, uh, calculate the mass of the product.
Okay, so you write the balance equation first. So 2 mg plus O2 equals 2 MgO, you saw it before. So 3 grams of Mg equals to 3 over 24 because magnesium is 24, right? So 3 grams of it is just 0.25, 125 moles. of magnesium. So the mole ratio between Mg and MgO is 2 to 2, or if you simplify it, is 1 to 1. So therefore, 0.125 moles of Mg will form 0.125 moles of MgO. So mole ratio is the ratio of big, quote unquote, big numbers in front of the reactants and products inside the equation. Yeah, in this case, Mg and MgO both have a number 2 at the front. So the ratio is just 2 to 2 or 1 to 1. So 1 mole of Mg is 1 mole of MgO. So if the, let's just say if the ratio is 1 to 2, so 1 mole of Mg equals to 2 moles of MgO. So if 1 Mg is 0.25 moles, MgO will be 0.25. Okay. So since 0.125 moles of MgO is formed, the mass we can calculate it via the equation 1, which is 0.25 times 24 plus 16 equals to 5 grams of MgO is produced from 3 grams of magnesium in excess oxygen. So now we will do moles and volumes. Yeah. So number of moles of gas equals to volume of gas, decimeter cube, at RTP divided by 24. So Wilbert, can you please say the first example and the two examples here? The two, yeah.
First example is calculate the amount of moles of oxygen molecules in the following volumes of oxygen at RTP. Number 1, 48 dm cubic meter equals to 48 dm per cubic meter over 24 dm cubic meter equals to 2 moles. And number 2 is 3.6 dm cubic meter equal to 3.6 dm cubic meter over 24 cubic dm equals to 0.15 moles.
Okay. So you just divide, yeah. So divide the, yeah. So
Yes,
like example two,
just divide.
yeah. So now Owen, can you please read us example number 2?
So example number 2. Calculate the amount of volume of oxygen at RTP for each of the following masses of gases. Okay, so do not be confused. This is simple. First, figure out the number of moles of oxygen. Now, simply add the mole equation 2, and you are done.
So how we do it is 320 grams, because we have 320 grams. We divide that by 32 equals to 10 moles times 24 decimeter cube equals to 24. Because oxygen will always be 2, so oxygen will always be, because O2 equals to 16 times 2, which is 32. So that's how you get the 32 down there. And then 320. Yeah. So now example number 3, calculate the volume of oxygen at RTP required to burn 1.4 of butane. So this is the balanced chemical equation will most likely be provided. C4H8, which is butane, plus 6O2, which is oxygen, equals becomes 4CO2 plus 4H2O. So the way you approach it is very similar to example 4 of the reactive mixes before, which is, yeah, before. And then to calculate the volume of oxygen required, all you need to know is the moles of the oxygen that is required, and we know the ratio of butane to oxygen is 1 to 6. That means for every mole of butane, there will be 6 moles of oxygen. All we need to know then is the amount of moles in 1.4 grams of butane, which is Pretty easy. So 1.4 grams of butane equals to 1.4 grams divided by 4 times 12 because carbon carbon is 12. You multiply that by 4 because there's 4. And then 1 times 8 because hydrogen is 1 for the atomic mass. You multiply by 8 because there's 8. H equals to 0.0259 moles. So 0.0259 moles of butane requires you multiply because it will always be 3 significant. So 0.025 times 6 because it's the ratio is 1 to 6. Moles of oxygen due to the 1 to 6 mole ratio is equals to 0.15, 0.15 moles of oxygen. So 0.15 times 224 decimeter cube is cubic decimeter so equals to 3.6 cubic decimeter. That is the volume of oxygen required. So now we're gonna continue to moles and concentrations. So moles solute equals concentration times volume. So Owen, can you please tell us the first example? And if you see this that up arrow to 3, that means it's powered by 3.
Okay, thank you for your explanation. Okay, example, the first example. Uh, Calculate the volume of sodium hydroxide concentration, uh, 0.16 moles per tm bar of 3 r cubed. Yeah, needed to neutralize 20 centimeters cube of sulfuric acid concentration 0.2 moles over tm cube.
So this is the
Yeah,
balanced chemical
the balance
equation.
equation.
Nice, okay, I'll just do it. So the balanced chemical equation is 2NaOH plus H2SO4. It becomes Na2SO4 plus 2H2O. So we calculate the amount of moles in sulfuric acid. The ratio is 1 to 2 for 1 mole of sulfuric acid. There will be 2 moles of sodium hydroxide required. So once you figure out that, which you figure the required amount of moles of sodium hydroxide, so we can easily obtain the volume by rearranging the formula. So remember, Cm cube needs to be converted into dm cube by dividing by 1000. So moles of sulfuric acid equals to 0.2 times bracket 20 divided by 1000 to make it decimeter. And we bracket equals to 0.004. And then moles NaOH equals to, so the for sodium hydroxide 0.004 times 2 equals to 0.008. So volume of NaOH equals to 0.008 divided by 0.16 equals to 0.05 decimeter cube or cubic decimeter. Wilbert, can you please read the first all of this for percentage yield?
Percentage yield. In a chemical reaction, the expected or calculated amount of product is the or theoretical yield. Unfor- Unfortunately, however, the product amount actually produced, which is the actual yield is often lower than this theoretical amount. Taking a ratio of these two values gives us the percentage yield. The formula of percentage yield is percentage yield equals the actual yield over theoretical yield.
Okay, so first example, excess magnesium carbonate was added to 25 cubic centimeter of sulfuric acid. Concentration of 2.0 moles per decimeter cubic decimeter. The unreacted magnesium carbonate was removed by filtration. The solution of magnesium sulfate was evaporated to give 6.7 grams of hydrated magnesium sulfate crystals. Calculate the percentage yield. Balanced chemical equation is as follows. Now, Owen, can you please read the rest?
Excuse me. Wait. Uh, the mass. Uh, yeah, the mass, right? Uh,
Yes.
so the mass. Yeah, so the mass equals. Uh, yes, the mass, right?
Yeah, you just need to say just do this. Just do this one.
Okay. So
Yeah.
yeah.
And
So
yeah,
the
yeah, yeah.
so the mass is mgco subscript 3 plus h subscript 2 s o subscript 4 to uh, mgso subscript 4 plus co subscript 2 and h2o h subscript yeah h2o mgso subscript 4 plus 6h subscript 2 O to mgh as O subscript 4 of is that times yeah of 4h2o.
Okay, so did you stop you just did this one, right? This long equation, right?
Yeah.
Okay. So the question tells you that 6.7 grams of the crystals were formed, so therefore this is the actual yield. The theoretical yield can be calculated like this. So moles of H2SO4 goes to 25 divided by 1000 to make it to decimeter cube. Multiply by 2 equals to 0.05. Moles of MgSO4 multiplied by 7H2O equals to 0.05. Thus the mole ratio is 1 to 1. So relative formula mass MgSO4 times 7H2O equals to 246. That is the yeah that's the formula mass. So mass equals to 0.05 times 24.6 equals to 12.3 grams. Yeah, which is the theoretical yield. And how to get the percentage yield is by dividing the 6.7 which we got here. And then you divide it by the 12.3 we got here equals to 0.045 or 0.545, which is in percentage 54.5. So the original answer is in decimals. To convert the decimal to percentage, just multiply by 100. So purity. So percentage purity equals mass of pure substance divided by total mass of sample. So example, 7.0 grams of impure calcium carbonate was heated and 2.42 grams of carbon dioxide was collected. So calculate the percentage purity of the calcium carbonate. So the chemical equation CaCO3 equals to CaO plus CO2. So the key here is that carbon dioxide can only be made from pure calcium carbonate. So the impurities in the original sample of 7 grams will not contribute to the production of carbon dioxide. So how we get the percentage purity can be calculated as follows. Wilbert, can you please read the first 3 bullets, which are these ones? And Owen, can you please read the last two?
moles,
Yeah,
which is
wait.
CO2, equals to 2.42, or 12 plus 32 equals to 0.055. Moles, which is CaCO3, equals to 0.055. The mole ratio is 1 and 1. The formula mass of CaCO3 is 100.
Mass pure CaCO3 equals to 0.055 times 100 equals to 5.5 grams. Uh, Percentage purity equals to 5.5 over 7 equals 0.786 or 76.6%. 78.6%, sir.
Okay, so now empirical and molecular. So example, hydrogen contains 92.3% carbon and carbon yeah, and 7.7% of hydrogen. So relative molecular mass is 78. Calculate empirical and molecular. So percentage composition, carbon 92.3, hydrogen 7.7. So we divide the AR, just the relative atomic mass of respective element. So carbon is 12. So 92.3 divided by 12, we made the percentage into grams, so we can multiply it. So it's 7.69 moles. Hydrogen 7.7, and hydrogen has 1 for relative atomic mass, so we divide that equals to 7.7 moles. And then we divide both of them by the smallest one, which is 7.69. We divide both of them, so we simplify it to make it to 1. So the ratio of carbon to hydrogen therefore is 1 to 1. So empirical formula is CH. The molecular formula is a multiple of empirical formula of the empirical formula. The MR of the hydrocarbon is 78, and the MR of our empirical formula CH is 13, giving us the multiple of 6. Because if we divide 78 by 13, yeah, we get 6, right? So molecular formula is thus C6 and H6. So that is the end of the day. Yeah.